Chapter 6, the final chapter that we will be looking at this semester. So let's go ahead and get started. Section 6.1, graphing systems of linear inequalities in two variables. So the first thing we are going to look at is graphing linear inequalities. We should all know how to draw a line at this point based on a given linear equation. So, because we know how to do that, we can also graph linear inequalities as well. The only thing we have to know is, well, two things. The two things we have to know would be if the inequality symbol is less than or equal to or greater than or equal to, we're going to make that line solid. If the inequality symbol is less than or greater than, we will make it a dashed line, which is indicating that the line is actually not part of the solution region. Speaking of solution regions, that's the second thing we need to be able to do. Shade the appropriate solution region. So there are a couple different ways to do that. The way we're going to do it is we're going to pick any point not on the given line. Then what we're going to do at that point is plug it into the inequality. And if you get a true inequality, then you will shade the region that contains that test point. If you get a false read, then you're going to shade the region not containing the test point. Let's take a look at some examples to see how this works. Example number 1. What we were trying to do here is find the graphical solution of this inequality. Well, remember that we're looking for all possible points. So the ordered pairs, x comma y, that would make this inequality true. So here's how we're going to do this. We're going to add 8 to both sides. And that's going to give us what? 4x is less than what? 8. Okay. At this point, we're going to divide both sides by 4. It's positive, so we keep the inequality symbol the same. And we end up with this. X is less than 2. All right, so from what we just talked about, this is how we're going to graph it. You need to understand that, again, we're looking at this being graphed within our Cartesian coordinate plane system, okay? So first thing I want you to do is think about what this would look like if it were just a line, and in other words, an equation. So if this said x equals 2, you'd have a vertical line right here going through the point 2, 0, right? But it doesn't say that. It says x is less than 2. So we're not going to draw in this vertical line solid. We're going to make it comprised of a series of dashes. So let's go ahead and do that. Again, I'm making this line with a series of dashes because of the inequality symbol. It's less than. I'm going to go ahead and define this equation as x equals 2 because this line is really representative of x equals 2. And the next thing I'm going to do is look at the inequality symbol. It's less than. All right, so if you picked 0, 0 as your test point, this is a point not on the graph here, then do you see it, that 0 is in fact less than 2? That does give you a true statement. 0, if x is 0, it is less than 2. Therefore, you're going to shade everything to the left of this dashed vertical line. And this shaded region is representative of your solution. Example number 2. We're doing the same thing. In this example, we're trying to determine the graphical solution of this inequality. So this is a little more difficult. I mean, it's it's a linear inequality that now consists of two variables, x and y. So one thing we can do here is this. Let's determine the intercepts of this line. All right, this is something we should be able to do with any equation. All right, so if I'm going to try to determine the x-intercept, what am I going to do? Well, the x-intercept is always determined when you do what? You let y be equal to 0. So if y is equal to 0, our x-intercept would be what? Well, determined based upon this equation. Again, x-intercepts are determined by letting y equal 0, which would just give me this equation. So this is telling me that x should be what? X should be 3. All right, so we know that this point 3, 0, which is our x-intercept on the graph of this line, is going to be a point on the graph of this line. So I'm going to put a point right here at 3, 0. All right, 1, 2, 3, 0. And then the next thing we can do is determine our y-intercept. Okay, so our y-intercept is going to be 0, comma something. All right, so what does this mean? To determine the y-intercept, you let the x be equal to 0. If x is 0, then you are left with this, negative 3y equaling 15. So therefore, you solve this for y and you get negative 5. So 0, negative 5 is your y-intercept. So let's go. Negative 1, negative 2, negative 3, negative 4, negative 5. All right. So now we've established 2 points that would be on the graph of this line. All you got to do now is connect the dots. It would be nice to use a straight edge here, but you know, just do the best you can if you don't have a straight edge. I'll just do that now. So let me think about this. Let's see. It's going to be pretty challenging. Let's see what we can do the best we can here. All right. So here's what it's going to look like. Is it going to be solid or dashed? It's going to be solid because it contains the or equal to component. So let's go to work. Ooh. So close enough. Again, if you have a straight edge, probably be better. But anyway, I have my line here, and now what I'm going to do is come up with a test point. I'm going to again test 0, 0. All right. I'm testing the origin. Okay. So if you were to replace the x and the y here with 0 and 0, would you get a true statement? Is, in other words, 0 greater than or equal to 15? Is 0 greater than or equal to 15? No, it's false. So that means the entire region that does not contain 0, 0 will be shaded. So again, the shaded region represents the solution, okay? And then it'd probably be a good idea to put your ordered pairs here so we can clearly define what the heck's going on. This point will be what? 3, 0. Okay?